Welcome back to another explainer. Today, we're diving straight into what is honestly one of the greatest scientific detective stories of all time. A story that fundamentally altered our understanding of the universe and literally unlocked the entire modern electronic age. We are looking at the Cathode Ray Discharge Tube. This isn't just some dusty piece of old lab equipment, it's the very stage where scientists first caught a glimpse of the microscopic building blocks of our reality.
Think about it for a second. How exactly do you catch a culprit that leaves zero physical fingerprints, makes absolutely no sound, and is totally invisible to the naked eye? Well, that's the exact historical puzzle scientists were staring down just over a century ago. Before we truly understood what made up an atom, researchers had to design incredibly clever traps to force these hidden components to finally reveal themselves.
Okay, let's dive into this. Part 1, the spark in the vacuum, the initial mystery.
So to crack a microscopic case, you obviously need the ultimate magnifying glass, right? Enter the cathode ray discharge tube. It sounds super complicated, but it's basically just a sealed glass tube with a metal electrode shoved into each end. They pump out almost all the air inside and then, bam, hit it with a massive jolt of high-voltage electricity, and suddenly, these wild, mysterious rays just shoot right through the middle.
Now, to really appreciate how mind-bending these mysterious rays were, we kind of have to rewind a bit. For practically all of the 1800s, everyone thought the atom was the absolute end of the line, just a solid, indestructible, indivisible little billiard ball. But by the late 1800s, scientists started noticing that when you push electricity through low-pressure gases, things get really weird. The gases behave in totally unexpected ways. This perfectly laid the groundwork for 1897, when a physicist named J.J. Thomson decided to actually investigate these rays, and in the process, flip science completely on its head.
Let's move to and see how this builds. Part 2, building the discharge tube and setting the trap.
All right, so how do you physically build a trap for something you can't see? You need very specific gear. It starts with that long glass tube, totally sealed off from the outside world. Inside, you've got your two main players, the cathode, which is your negative electrode, and the anode, the positive one. Hook all that up to a vacuum pump to control the environment. And finally, bring in the heavy machinery, a massive high-voltage power source ready to blast electricity across the gap.
But here's the absolute kicker. The real secret sauce, 0.01 millimeters of mercury. That is an insanely low number, and it represents the internal gas pressure left over after that vacuum pump has done its job. By sucking practically all the air out of the tube, the scientists essentially created a blank canvas. This ultra-low pressure is crucial because it allows the electricity to zip straight through the trace amounts of remaining gas without crashing into a bunch of pesky air molecules along the way.
Okay, let's fire this thing up step by step. First, the vacuum pump yanks the air out, dropping the pressure. Second, you flip the switch on that high voltage. That's the trigger. Third, because the conditions are so extreme, that tiny bit of thin gas actually starts conducting the electricity. And boom, step 4, the magic happens. These completely invisible rays erupt out of the negative cathode, race across the tube toward the positive anode, and slam into the glass wall at the far end, causing it to violently glow or fluoresce.
Moving right along to Part 3, decoding the invisible rays. It's time to examine the physical clues left behind.
So, the scientists are staring at this glowing patch on the glass opposite the cathode. But what exactly were these glowing rays? Were they just some weird glowing gas? Or maybe a brand new form of light? To figure it out, they quite literally started putting physical obstacles right in the middle of the ray's path.
And the mechanical evidence they got back was mind-blowing. First off, when they put solid objects in there, the rays cast perfect, crisp shadows behind them. That tells us they travel in dead straight lines. But the real smoking gun is this next point. If you place a tiny, lightweight paddle wheel in the tube and the rays hit it, the wheel actually starts spinning. I mean, ordinary light doesn't push a paddle wheel like wind pushes a windmill, right? For that wheel to spin, whatever is hitting it absolutely must have actual physical mass.
Okay, so they travel straight and they have mass. Let's dig into the next set of clues, which deal with the immense amount of energy these invisible projectiles were packing.
The energy evidence was undeniably huge. When these cathode rays slammed into metal surfaces inside the tube, they generated a ton of heat. And when they hit certain materials, like the glass walls of the tube itself, they produced that crazy, brilliant fluorescence. That glowing region was essentially the visible footprint of our invisible culprit, proving beyond a doubt that these rays carried a massive energetic punch.
Naturally, the scientists next wanted to know if these rays carried an electrical charge. So they applied external electric and magnetic fields to the tube. And this brilliantly illustrates the big breakthrough. When an electric field was applied, the straight path of the rays suddenly curved, bending directly toward the positive plate. You know the rule, opposites attract, so this undeniably proved the rays were negatively charged. They also saw the path deflect under a magnetic field, which basically sealed the deal on their electrical nature.
But wait, this right here is the ultimate clue, the true game changer. They decided to swap out the gas inside the tube. They'd pump out one gas, pump in a totally different one, crank up the voltage, and guess what? Nothing changed. The rays behaved the exact same way every single time. They had the same mass, the same negative charge. This meant the particles making up these rays didn't just belong to one specific gas. They had to be a fundamental building block present in absolutely all matter.
All right, part 4, discovering the electron. Let's look at the final verdict.
So it's 1897, and J.J. Thomson finally pieces all these wild clues together. He looks at the sharp shadows, the spinning paddle wheel, the magnetic deflection, and the fact that the gas type didn't matter one bit. He logically deduces that cathode rays definitely weren't light, and they weren't just energized gas either. They were a stream of tiny, negatively charged particles. He successfully caught the culprit. He ultimately named these universal particles electrons and proved they exist hiding deep inside every single atom.
And with that single monumental realization, the old scientific paradigm totally shattered. The atom was no longer the smallest, solid, indivisible chunk of the universe. Thomson proved that atoms are in fact divisible and contain these smaller, negatively charged particles. He practically cracked open the atom and found a whole new microscopic world inside.
Which brings us to part 5, impact on the modern world, the legacy of discovery.
Now you might be wondering, why does an experiment from 1897 actually matter to you sitting here today?
Well, because harnessing that tiny electron directly birthed the technology of the 20th century.
That exact same glass tube experiment evolved straight into consumer tech, like the old cathode ray tube televisions. You know, the giant bulky TVs many of us grew up watching. In medicine, it laid the critical foundation for advanced medical imaging devices. And in science, it led to oscilloscopes and incredibly precise electron beam instruments that researchers are literally still using today to push the boundaries of physics.
Of course, as with every single piece of technology, there's always a trade-off. The advantages of the CRT were obviously world-changing, discovering electrons and establishing the entire foundation for modern electronics. However, the limitations were strictly physical. The original CRT tech requires massive amounts of high voltage to operate, and it heavily relies on fragile, super heavy glass tubes to maintain those low-pressure vacuums. That's exactly why those heavy, boxy TVs have largely been replaced by the sleek, lightweight, modern flat screens we use today.
So the crucial point is this. The cathode ray discharge tube was way more than just a weird glass oddity sitting in a Victorian lab. It was the crucial tool that proved atoms are not indivisible. It didn't just show us the electron, it literally laid the foundation for modern atomic theory and the entire modern electronic age. Think about it. We've gone from genuinely believing the atom was a solid block to precisely controlling the flow of invisible electrons to power everything from our smartphones to spaceships. It's incredible. And it really begs the question. The electron changed everything. So, what invisible particle will we harness next? Thank you so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.